Hello, my name is Chris Sakery, and I represent the IM group consisting of Megha Goel, Jeff Putt, and Christian Iyer. For the next 7 minutes or so, I'll be talking about the history, current state, and future of information storage technology. Researchers can now store information using only 12 atoms. To understand this remarkable innovation, it is useful to learn about the events and disruptive technologies that led to it. We can go back 30,000 years to the cave paintings in what is now called the Chauvet Caves in France, where Paleolithic man used charcoal on cave walls to paint beautiful portraits of the animals well known to him. These paintings are the earliest known surviving instances of where man has used the outside world to store thought. From an information theory perspective, Paleolithic man was thinking of an animal in his mind, the sender. He used his arms, hands, and charcoal pieces to draw, in code, that image of the animal, the message, onto the cave walls, the medium or channel. To put it another way, Paleolithic man used charcoal in caves to store information. While information storage technologies have changed dramatically over the past 30,000 years, the basic concepts of information theory remain the same. Other forms of early storage technologies are Sumerian cuneiform, Chinese knotted rope, and Egyptian papyrus. A quick overview of recent information storage technologies includes now defunct magnetic drum memory and punched cards. Technologies that are showing signs of market decline are magnetic tape, floppy disks, and cassette tapes. Even CD and DVDs are showing the telltale signs of waning end-of-life technology. The magnetic drive has been the mainstay in information technology for the last 4 decades. Both the cost and storage capacity, two prime characteristics, seem to loosely follow Moore's law in that they halve in cost and double capacity approximately every 2 years. Market forces are demanding that data devices store ever-increasing amounts of information, be affordable, and perform very quickly. In order to satisfy all these demands, devices need to pack the information as tightly as possible. The tighter the data is together, the more information you can store in the same place, the less distance the read-write head has to travel, and the less material is required to store information. As expected, areal density also trends very closely with Moore's law. This trend appears to be sustainable only through progressively disruptive innovations as depicted in the S-curve patterns seen here. Cassette tapes use ferric oxide to store information, but were disrupted by the thin film heads. IBM, Memorex, and Storage Technology switched to the thin film technology earlier, but there is little evidence that these firms enjoyed sustained first-mover advantage. Magnetoresistive heads displaced thin film technology and enjoyed much success as the main underlying hard drive technology for well over a decade. Seagate achieved the highly coveted 1 terabyte per square inch density in 2012 by employing heat-assisted magnetic recording, or HAMR. Some researchers believe HAMR could increase the limit of magnetic recording by more than a factor of 100 and continue the pattern of punctuated equilibrium that drives the sustained trajectories. This could result in storage capacity as great as 50 terabytes per square inch. Other engineers are not as optimistic about the future of magnetic drives and think they are quickly reaching the areal density limit. Magnetic drives use spinning platters to store information. In order to increase the capacity, engineers must increase the number of spinning disks and the rate of spin, but there are limits to both strategies. Solid-state drives use transistors to store and retrieve information much faster than magnetic disks. Solid-state drives appear to fail less often, operate faster, but are currently 10 times the cost of magnetic devices. Scientists are now able to store information using just 12 atoms per bit. The information is stored by manipulating the magnetic properties of the atoms. These states can be changed by very quickly in less than 5 nanoseconds, or 5 billionths of a second. This also allows an enormous amount of data to be stored in a very small place because the data has such high areal density. In order to maintain a stable 12-atom pattern, the atoms must be magnetized differently than usual. Most magnets align their magnetic properties along the same direction. Examples include directional compasses, refrigerator magnets, and conventional magnetic storage devices. These 12 atoms are magnetized in the opposite direction in order to keep their pattern stable. This unusual magnetic alignment is called antiferromagnetism and is what makes this technology work. Seen here is the word think, as it would be stored using the 12-atom nanostorage techniques. Each white and blue dot represents one atom. This requires only 480 atoms to store the entire word, where previously over 1 million atoms were needed to store each bit. Should this technology go commercial, it would have dramatic impacts. Successful implementation of the 12-atom storage technology will drastically cut the hardware requirements for data storage, driving the cost of data even cheaper, encouraging people to store even more information. Surveillance systems could record information for a longer period. This additional data could solve crimes more efficiently and with greater certainty, and perhaps reduce crime rates. Surgeries and other medical procedures could be recorded at levels not previously possible, and could lead to a dramatic improvement in healthcare and our quality of life. The nanomaterials used in nanostorage may greatly reduce the current environmental impacts of electrical-mechanical waste. Information storage has been the bottleneck in most systems, but this technology may change that. It is likely that CPU processing speeds may need innovations of their own to keep up with the increased amount of data to process. The same could be said of both wired and wireless data transfer methods because of the increase of data demand. We will need an even faster, more accurate search algorithms so that people can find useful content from the exponentially growing library of Babel. Man began using the outside world to store his thoughts with charcoal in caves. As his need to store data and recall information increased, so did the need for more suitable information storage devices. It was through the creatively destructive process of disruptive innovations that allow us to now record our thoughts on atoms, the very fabric of our universe.